Let's start by understanding what the fundamental frequency is. It's the lowest frequency at which a standing wave can form on a string or similar medium. In this situation, the two ends of the string are fixed, which means these points don't move and are called nodes. The string length, denoted as L, fits exactly half of a wavelength, so the wavelength is twice the length of the string. This relationship helps us see how the string's length controls the frequency of the wave, establishing the basic wave pattern that we call the fundamental frequency. The harmonic series consists of frequencies that are integer multiples of the fundamental frequency, which means each harmonic corresponds to a whole number times the base frequency. When we look at a string fixed at both ends, the pattern formed by its vibrations shows a number of loops equal to the harmonic number. In these patterns, nodes are points where the string has zero movement due to destructive interference, while antinodes are points of maximum movement caused by constructive interference. For example, the first harmonic shows one loop with nodes at the ends. The second harmonic has two loops. The third harmonic, three loops, and so on, each increasing the frequency and complexity of the wave pattern. This visualization helps us understand how musical tones are built from simple vibrations. Here we see the lowest three natural frequencies, or harmonics, of a guitar string. The first harmonic has 1/2 of a wavelength fitting into the length of the string. By rearranging the equation, we find that the wavelength is twice the length of the string. The second harmonic fits a full wavelength across two segments of the string, so the wavelength equals the string length. For the third harmonic, 1.5 wavelengths fit into the string length, making the wavelength 2/3 of the string length. These relationships help us understand how different frequencies and tones are produced by vibrations along the string. When we look at standing waves in pipes, we can see two main cases based on the boundary conditions: pipes that are open at both ends or fixed at both ends, and pipes that are closed at one end and open at the other. In an open-open or fixed-fixed pipe, the boundaries are in phase, meaning both ends are either nodes or antinodes. This setup allows all integer harmonics to form, with the fundamental wave fitting half a wavelength within the pipe length. On the other hand, a pipe closed at one end and open at the other has boundaries that differ, a node at the closed end and an antinode at the open end. This configuration only supports odd harmonics, and the fundamental wavelength fits 1/4 of a wave into the pipe. These differences in boundary conditions directly affect the harmonics and fundamental frequencies that the pipe can support, which is important for understanding how musical instruments and other systems involving pipes produce sound. When we look at an open-closed pipe at its fifth harmonic, the displacement of air molecules shows a node at the closed end because the molecules can't move against the solid wall, and an antinode at the open end where the movement is at its maximum. In terms of pressure, the pattern reverses. There's an antinode at the closed end where pressure variations reach their peak with maximum compression and rarefaction, while the open end holds a pressure node where the pressure stays constant and equal to atmospheric pressure. It's important to note that the pressure and displacement waves are out of phase by 1/4 of a cycle, meaning when one reaches its maximum, the other is at zero. This relationship helps explain how sound waves behave inside the pipe, showing compression where displacement is minimal and vice versa. Here we can see how pressure and displacement vary within an open-closed pipe at different points in time during the fifth harmonic. At one moment, labeled A, the pressure shows alternating regions of compression and rarefaction, with corresponding displacement patterns that are out of phase with pressure. 1/4 cycle later, in B, the displacement is momentarily zero throughout, while pressure remains steady. Half a cycle after the initial moment, shown in C, the pattern reverses with pressure and displacement waves flipped compared to the start. This illustrates the dynamic relationship between pressure and particle movement inside the pipe as the sound wave oscillates, helping us understand how standing waves form and behave in air columns.